If I put a B here, a C here, and an A here, what do those laws stand for? This one stands for Boyle's law. This was Charles' law. This was Avogadro's law. How they all link volume with something else. In Boyle's case, pressure, inversely proportional. In Charles' case, temperature, directly proportional. In Avogadro's law, number of moles, or N, also directly proportional. Now, there's a cool thing that we can do with a proportionality symbol like this. We can say volume has this proportional relationship with pressure, volume, and temperature. And so we can say volume, we can combine pressure, temperature, and number of moles like this. So pressure is directly proportional to number of moles and temperature, and inversely proportional to pressure. So we're actually getting close to now having one equation that will have all four of those variables. Now, we said before we can replace that proportionality symbol with a constant, and we're going to do that, and this is what it would look like. It would say that this has to be the relationship for a gas, that it's pressure times its volume divided by its number of moles, also divided by its temperature, is equal to some constant, as long as that gas is what we say behaving ideally. Is that not cool or what? That has consequences. So we're going to actually change that generic K, if it's okay with you, to a capital R. And I think at the end of part 1, this is part 2, at the end of part 1 we said that R is actually the ideal gas law constant. So this is not usually, we're building up to what we call the ideal gas law equation, and this is one form of it, but usually you're going to see the ideal gas law equation written this way. To me, if we cross multiply, okay, we end up with something like this. PV is equal to nRT. It's the same equation you saw before, just flattened out. So this is your ideal gas law equation. Where we've been talking about P is pressure, V is volume, N is number of moles, R is the ideal gas law constant, which I'm going to give you a number here for what that value is, and T is temperature. So this actually links for a gas how those four variables with the ideal gas law constant. We've been talking a lot in here about units, and we said that your units need to cancel and make everything right. There's actually different values for the ideal gas law constant depending upon the units you use for P, V, N, and T. But assuming that we use pressure in units of atmospheres, volume in liters of liters, N in number units of moles, and temperature in, of course, has to be units of Kelvin, then the way this works out is R will take on a value of 0.028058, and the units of R will be liters, atmospheres in the numerator, divided by moles, Kelvin in the denominator. Let's take a quick look at this, if that's okay with you up here. So I'm going to take pressure and volume, and instead of a number, I'm going to put in their units. Well, I'll just put it underneath here. So pressure, we said, is going to be atmospheres. Volume, we said, was going to be liters. Of course, N, the units are moles. R, we said the units are down here. Liters, atmospheres per mole, Kelvin. And of course, temperature is going to be units of Kelvin. I'll go ahead and put moles in Kelvin over 1 if that's okay with you. See if I can pull up a different color right quick. So let's see what cancels. Moles cancel with moles, kelvins cancel with kelvins, and we actually have units of liters, atmospheres, and atmospheres, liters. So our units check out. They are equal. So what's what we say? Dimensionally consistent. In the next few, I'm going to finish up this this part, then actually using this relationship, the ideal gas law equation. And we're gonna, if you've done much with physics, all it is you plug in, you'll know 3 of these, 3 of these 4 different variables. You plug in the 3 that you know and solve for the one that you don't. So we're gonna do some problems like that.